So we are starting the recording, and today we will be introducing fermions. And the idea will be to switch from the fermions land back to Grassmann's land. And probably that's something that people are more easily familiar with. So for Grassmann's, we started with the anti-commutation relation, GK. And that was always 0, which means that they were anti-commuting symbols. And I will introduce fermions today by taking other symbols. I will denote them by M, and I will demand that they will be also anti-commuting. MJ, but I would put them now, I think, to 2 delta J. This 2 is something that it's just a matter of rescaling. Okay, so GK for us are Grassmann numbers. Double S, double N numbers. And in physics, we relations like this we call Majorana operators. So I'm putting N. And the difference is the homogeneity versus the identity. So I will put it in color. So here we have something with a 0, and here we have an anti-commutation, which is almost always 0, unless those fermions are in the same spot. And to make it precise, we should add that there will be a notion of Hermitian conjugation, and that basically they are self-adjoint like this. So this is a little bit a different space. And now I was telling you different views on Grassmann numbers, and the views on Majorana operators will be on the basically one way of viewing them. And what we can still construct is the fermionic. So those relations are called Grassmann relations. Those relations are sometimes called Clifford algebra. So sometimes people say Clifford for that as well. And then what I want to construct now is canonical anti-commutation relations. Commutation relations. So car, and here I will again be working with JK from 1 until even to L, and I will be defining FK to using those notations that I was also introducing in the additional videos. So the odd part and then the even part. And here the K will be going from 1 until L without the 2. Okay. And now those FK operators, they will have also an adjoint operation. And here I will have FK Fj is delta JK if there is a dagger. And if there's no dagger, Fj Fk, then this is 0. Those two relations are independent. And what we will show now is that there is an easy linear transformation on generators that relates those algebras. And that's why those relations are independent, because here we have basically 2L squared relations, yeah, for any choice JK into L. And here we have somehow a little bit fewer, it seems. So let's look at that. First of all, what I can do is the adjoint of 0 is 0. So let's look at what happens if I take the dagger of the anti-commutator. And that's nothing else than Fj Fk plus Fk Fj dagger. And I view them as matrices. So basically the first one will be Fk dagger Fj dagger plus yeah, fj dagger, fk dagger. So I get from this the anti-commutator of the adjoints. So these two, so basically this and this is related, yeah? I can derive one from the other, so I'm not putting the daggers here. Okay, another thing is that if we want to do representation theory for this, so this is something that I will only mention in the passing, but basically we need to postulate that there is a state, psi, such that for all k from 1 until L, this state is in the joint kernel of fk's. So f0, so we can write this that phi is in the intersection from k1 until L, kernel of fk. The next thing that I want to show is that basically we can build a full basis. I will call it mu. And then because it's in the kernel of the other operators, then I can use the daggers to say, to have something non-trivial. Maybe I will start from one. One dagger, mu1, until fl dagger mu l. Sorry, this is mu. And I will be applying this operator to the vacuum, right? To vacuum. And this should be non-zero. And now if we do the counting, then the span of C of all those states mu as before is a string of 0, 1 numbers, which tells you whether you have this creation annihilation operator there. So basically number of mu's is 2 to power L, because I have two choices for each. And the span of this is C to power 2L. So basically we have this space. So this space you could also view as computational basis states of qubits. Okay. Okay, so that was a little bit fast, but let's recap. We have three different algebras, and we need the F operators to tell you what is basically the adjoint, because we can construct here the Hilbert space using those dagger operators. So F operators we would call annihilation operators of fermions. And F dagger is creation operators. And we see that we are implementing the Pauli principle, because if I evaluate this for j equals k, it's telling me that 2 times fj squared, maybe fj dagger squared, is 0. So if I apply fj dagger squared to vacuum, I will get 0, which is called the Pauli exclusion principle. So we see that this is implemented here in the algebra. That's useful because this allows us to say what happens if I take the dagger of okay, let me make a new page to say what this is telling us. So this relation between fk's and mk's is useful because we can learn a little bit more about these operators. While those fk's I was doing quite fast to say that basically fk squared is 0, so Pauli exclusion principle. Then we have the vacuum, and we can do the span of the space. So I can again use this notation with f mu in the same way as we had with G mu. So basically, like on the previous slide. So we have those, and this is a bit more intuitive, but now we can learn about MKs. And for example, I was saying that Fk is M2k minus 1. That's the consistent way of enumerating them when we are doubling the indices. And now what you see is that in some way you could say that M2k minus 1 is formally the real part of Fk, and M2k is the imaginary part of Fk. Why? Because if I take 1/2 of Fk plus Fk dagger, then I will get exactly that. So the question is in which direction you go. I was saying on the previous slide that Mk dagger is equals to Mk. Then I can know what it means to take Fk dagger. Well, Fk dagger means M2k minus 1, and then minus I, because complex numbers are have also the adjoint, and then you just keep the symbols like that. Okay, so we can do it that way. Yeah, so that's basically one way of viewing this. And then in the future, it will be useful to write it as matrices. So if I have Fk dagger, and I write this as a vector, then I could say that this is equal to a matrix, which will be 1i, 1 minus I. And then here M2k minus 1, M2k. And I can check the matrix multiplication that I will have M2k minus 1 plus I M2k, M2k minus 1 minus I M2k. So a vector of two operators here. So then we can generalize this F1 dagger all the way to FL dagger. And here I can write a big matrix. Let's call it big Xi. And this box takes from M1 until M to L, just lined up. And this matrix Xi has to be just a direct sum from k equals 1 to L of a 2 by 2 block. We had already 2 by 2 blocks before. I 1 minus I. So that's a way of transforming those Clifford relations to the CAR relations, canonical anti-commutation relations. Okay, so another way of viewing the adjoint is to say that we have the adjoint here in this linear space. So we could also go in this direction and arrive at that. So we could also treat F and F dagger as independent operators, and then we would get that M and Mk are self-adjoint. But one thing that I would like to derive, so I have this relation Fk on vacuum is 0. So another thing that we can derive as essentially a prop. So so we can define the trace of those F operators, and now we can look at Mk. What is the trace of that? And that will be useful for the talk today. So that's the main thing that I need. So basically, I was introducing Grassmann numbers, and all that I want is actually to go to those Majorana operators. But Majorana operators, I could just postulate, but it's useful to know how to take the trace of a Majorana operator, because that will allow us to make some useful formula today. And for this, I needed to define those F operators, which are basically a little bit like lifting it into a complex thingy. And so we view those Majorana operators as real and imaginary parts of those Fk operators. When I have Fk operators, then I also have the states. So I can sum over mu in the Boolean cube from 0, 1 to L. And then I can look at something like this. K mu. So what we want to derive is that this is 0. So how do we do that? Mu is basically f. I think we started from 1 until mu1. So whether this is 0 and 1, if we put a particular there or not, mu L, that's sort of the interpretation. So now if I apply mk to it, so applying mk to it, it's a little bit of a nasty computation, because either this will be fj plus fj dagger, or it will be minus I, and then 1/2 minus I half fj minus fj dagger applied to mu. And the conditions are that basically k is either 2j minus 1 or k is equals to 2j. Okay, so that's the kind of computation we need to do, which means that that this is splitting to 2 states, where I could define again eta j to be 0, 0, 1, 0, 0, and 1 is at position j. Okay, so what's going on? Basically, I will have, I could write this as 1/2 mu Boolean summation nj. And here I will have -1 to power, I will explain in just one moment what I mean, 2. And here, okay, so we will still need a phase. So let me do specific calculation. Specific. Let's say I have fj that I'm applying to mu. Okay, so what's going on? I have fj I still have, and then I have f1 dagger mu1 until fl dagger to power mu l applied to vacuum. So now what happens is that if I will push it through, each time I push it through, and some index k is not equals to j, then what we have is that the anti-commutator fj fk dagger is equals to 0. So they behave a little bit like Grassmann numbers before. I get a sign. So what I'm getting is -1 summation here from k smaller than j mu k. So I'm counting how many times fj encountered an f dagger operator. So I think I will run out of space, but mu1 until j -1 dagger. And then I have this fj. Then I have fj dagger mu j, and then dot 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 the remaining operators, not mu, vacuum. Okay, which means I'm pushing it through there. Here we have vacuum. So if I have k equals j, then I have fj dagger plus fj dagger fj is equals to identity, which means I'm getting this -1 to the summation k smaller than j mu k. And then I'm having 2 states here, right? So I will have identity minus the other stuff. So I will have f mu dagger without any change. I will not have f mu dagger because I will have the identity instead of j. So I will have here plus eta j, and here I will have delta mu j equals to 1. And then the other one is something where I can push it through, and I will just write plus 0, because once I swap these two at the cost of this identity, this is coming from the identity, then fj can anti-commute with the remaining ones, whether they are there or not, and it will hit the vacuum state at some point, and we will use the kernel condition. Okay, so that way I'm getting that fj applied to mu is, oh, this is not making sense. Sorry about this. This is already the cat. Yeah, I directly get the state. Mu nj, and this nj is removing mu j from it. Yeah. So so we are getting this state. Okay. So this is the computation. What happens if you apply a Majorana operator to those? And for the trace, we need to apply the Majorana operator to mu, and then take the sandwich. What happened here is that I'm changing the Hamming weight of mu. So mu is changing by 1 if I apply the f operator, and if I apply f dagger, I will change mu by 1 upwards. So they will not have equal numbers. So now we can make a simpler lemma. Let's say mu is non-zero. So maybe lemma. And the conditions that I was writing, then mu scalar product with mu prime is the Kronecker delta mu prime. So let's see how this works. Basically, I will have the vacuum state, and here f1 dagger mu1 until fl dagger mu l, and then I'm kind of trying to be extra careful here. I'm applying the dagger, and I will apply this full thing, mu1 prime until fl dagger mu l prime applied to vacuum. So I have the big bracket for the dagger here, and I have this here. So what I will be having is fl dagger. No, sorry, not dagger. Fl mu l until f1 mu1, f1 dagger mu1, then f2 mu2 dagger, and so on until fl dagger mu l prime, and here we have the primes. Okay, and those two are equal. So that's the definition of what happens, and I'm applying this to the side on the right hand side. You cannot just write I don't know, mu a mu for a non-Hermitian operator. So those operators are possibly non-Hermitian. So we need to say for which operator we apply it. But we have it. And now the thing that we should see is that the commutator of f1 dagger with fk dagger is 0 for k not equals to 1, which means I can push it through all the way to this side. And then I need to make a computation, another useful computation, f1 dagger on vacuum after I push it through. So I'm pushing it through without any phases. Then what we were saying is that this is 1 minus f1 dagger f1 applied to the vacuum, which means I'm getting again the vacuum, because this is dropping to 0 by the kernel condition. So so I did it once, and I singled out this pair of f1. Sorry, I connected them wrongly. Correction here. Okay, I have those two. The useful computation said that if M1 is equals to M1 prime, I'm getting the vacuum again. So it's a little bit like you wouldn't have those operators anymore. So you start reducing the problem. Another thing that could happen is that mu1 is equals to 1 and mu1 prime is equals to 0, which means you have only the F1 operator with no dagger, here no dagger, which means that you can just push it through all the way to 0 and it will drop. Okay, so now we are computing the case that if they are not equals, then we are getting a 0. If you have the other condition, then you could do it in the other direction and drop the other vacuum, which means that this is telling us that this will be proportional to delta mu prime. And this is telling us that when they are equal, so when we have mu and mu prime the same, then they are normalized. So this calculation gives us normalization. And this calculation gives us orthogonality. Okay, so from this calculation, we have computed that's my definition of the basis of this fermionic Hilbert space, that this basis is already orthonormal. Now I needed this because now I'm doing something more interesting where M will be acting on this or that. But what it will do is, what I was showing here is that it will always change mu to some neighboring mu. You will switch so-called occupation numbers. One of those entries in mu will change, which means that I can do this computation quickly, because this will be proportional to a summation mu, and it will be always something like mu binary with mu, all those non-zero things. Okay, so that's the computation, and so all this stuff is zero by orthonormality. Okay, so those were the useful calculations to kind of see what kind of computations we can do, but the proof is by orthonormality. And I will put the box because that's the full calculation. Then I would have to be much more careful with the indices to do this, but that's the basic idea. And I very much need this today. So once we have this, we can have some more fun and start computing other things. Okay, so we did half an hour now. The next thing that I will do is I will introduce Majorana words, which are just expressions like this. M2L, mu2L, which is equivalent to what we were doing for the Grassmann expressions, where I'm taking G1, mu1, and G2L, mu-L. Okay, another thing that we can show is that trace mu, maybe I will not say trace yet. Now we are coming to a cool proposition. Proposition mu. The Hilbert-Schmidt scalar product of mu with some other mu prime, they are orthonormal, d mu. And the proof goes like this. The scalar product is trace of mu dagger, mu prime. But now the cool bit is that they are self-adjoint, as I was showing, and tracelessness will come into play just now. So 2L dagger, we don't have any dagger, but I need instead M2L, M1 mu1 times M1 mu1 prime m to mu to prime, all the way until m to l mu to l prime, and we were taking the trace of that. Okay, so this is great because we know how to compute the trace. So I will put ... to say, okay, we just don't go into the details that we can split it. But once we go into blocks, we have mk mu k plus mu k prime, and then trace of that. Okay, because the idea is that I'm not showing that each of those Majorana modes is a little bit like in an independent product space, so the trace factorizes. I'm not showing it here. That would be a separate lemma that you would need to prove. I was showing this representation theory because from representation theory it's fast. Probably I will record a quick video. It's just 5 minutes of an additional discussion, but you see what's going on here. If mu k plus mu k prime is equals to 2, then we have mk squared, and we can compute that this is the identity. Why? Because we have the Clifford algebra relations. Mk prime is I did the okay. I can divide here by 2 to power l. No, I need 2 to power 2l probably. Because I was using a 2 here, k prime. So it means that k equals k prime. Then we have mk squared is equals to identity. So in this case, we have the identity, mu k plus mu k prime equals 0. Then we also have the identity, and trace of identity is equals to 2. If we have mu k plus mu prime k is equals to 1, then we have mk, and I was painfully deriving that trace of mk is equals to 0, which means that we have delta mu k prime. Here I need a factor of minus 2 to power 2l. And this is the identity of the, that one is the identity on the entire Hilbert space. So we need here 2 to power l, which means I need to remove here 2 to power l. And here I have 2 to minus l. That's just the definition of the Hilbert-Schmidt scalar product. And then I think it's almost done. No, but I shouldn't be splitting here. Okay, sorry. That's a different way. The splitting is sorry, something else. Once I have this together here, it's either m1 or it's either m1 or the identity. Those are the two different things that we can get. That's the computation that I did here. Sorry, I'm going back now. Which means that if m1 would be here, then trace of mk with whatever else is there would be 0. So we need to have this condition. And then once they are paired up in this way, product k, trace, then the only possibility, I still have 2 minus l, the only possibility is that this is trace of the identity on full Hilbert space, then 2 to minus l, which is just the normalization by definition, plus demanding that they are equal, mu prime. And that's the computation. Okay, so yeah, long story short, they are orthonormal. The Hilbert space that we are discussing, I was writing it down here. The Hilbert space is just this linear vector space here. So you can think of those Majorana operators as matrices. And now I have a set of operators that are orthonormal in the Hilbert-Schmidt basis, which means that I can express any operator, any linear operator on C to power 2 to power L I can write as x is mu starting from 0, 1, then Kronecker just regular Cartesian product, x mu, m mu. And x mu we can compute basically by taking the Hilbert-Schmidt scalar product of x with mu. The order might switch. So how if I do it on this side, x mu mu, yeah, looks fine. Which means that I have those operators. And now I can introduce the Bravyi dictionary. So from orthonormality, I can say that I can express any operator on the Hilbert space of fermions in terms of those Majorana words. Then I was already writing it here that as much as I can define a Majorana word, I can have a Grassmann word. So then what Bravyi did, I will put the link to the paper in the description. But Bravyi defined basically something which I will call Bravyi dictionary, where he said, let me define some linear transformation such that I will be defining this mapping. And that's the Bravyi dictionary. And the Bravyi dictionary is very cool because if you have the trace of two different operators, then you can write this as a Grassmann integral. So I will write only the result now here for now. So against P, against maybe G, and then I need to take omega into G of X and omega G, not G, omega G of Y. And then I need to have something like this P transposed with G. So this is where I wanted to get today. Basically, I wanted to introduce those fermionic algebras. I was consistently introducing different ways of forming different monomials in those algebras. And now it's kind of natural what happens when we introduce the Bravyi dictionary. So we say that this is C linear, and it's defined on those monomials to be mapping one to another. And suddenly I get a way of computing traces, because what is the trace of two non-commutative operators? It's Grassmann integration of P and G. And maybe I missed here this, but we will be proving the formula in next week. Basically, I have two operators, non-commutative. I multiply them together and I want the trace. Today we did a lot about traces. I was very fast, but basically those traces you need to compute sometimes, but now you can do it more symbolically, because for example, what we will be using next week is that trace of mu is equals to 0 unless for mu non-zero, for example, this kind of stuff. And now we know much more about traces. I have two non-commutative operators here. I will write down non-commutative. And what we get is a factor of -2 to power L, okay? Then integration PG. And for one of those operators, you go into G. And here you use the dictionary into Grassmann variables P. And then what you do is, this is, I will call it Bravyi trace kernel. Because this is the first time we see that Grassmann numbers are acting as Grassmann integration is integration, not derivatives, because this is a little bit like an integral operator. So in classical analysis, I could define a linear operator of a function f. So maybe let me label it by k. In such a way that I will get g of z, which could be an integral over numbers, over real numbers, for example, dz, and then k of z prime. f of z prime. So that would be an integral operator. And the same thing we have here where we get a really non-trivial thing by introducing an additional thing. We don't only have the operator y, here omega into p, and here x omega into g. And that's what I would call some kernel k. And suddenly we get a very non-trivial operation. We learn what is trace of xy. And just to give you an example, for example, if I want to compute an expectation value in some thermal state, then I would have trace a of e2 minus beta some Hamiltonian h divided by its normalization partition function here. And I could evaluate this by this pq, omega into g of a, and then omega into p of e2 minus beta h divided by z beta. And here's still ptg, the Bravyi kernel. And that's very non-trivial. So in principle, you can use Grassmann numbers to compute expectation values in thermal states. So that's why I was doing the trace today. We needed the trace to even motivate what's going on. And we have this integral transformation here. And the really new stuff that comes in today is that before we were integrating maybe against p e to exp of pt some matrix p. But today we introduced another stuff here. For example, we can introduce here pt some g, and then maybe we can have exp of gt m bar g. That's how this kind of trace could look like. And where we will need to be headed is to ask which kind of operators under the Bravyi dictionary are, for example, Gaussian operators, because we know how to integrate Gaussian Grassmann expressions. So this is where we are headed. Okay, so just a quick recap. Yeah, I will use the spotlight and go quickly. Anti-commutation with a homogeneous right-hand side is Grassmann numbers. Anti-commutation inhomogeneous into an identity, I call maybe Clifford algebra, but I additionally need that they are Hermitian. If they are Hermitian, I know what is the adjoint of such an operation here, and we can think of those F operators as real and imaginary part. This kind of relation, then I was writing this matrix because sometimes it's useful, but today it wasn't maybe so useful. But we will go back to it again. Then I was defining the vacuum state, which was used all the time. That's essentially the only structure we have. And we defined the basis. Once I had the basis, I continued to explain what happens to the trace, because the trace is basically the evaluation of the basis. So that's why we needed the basis. Then we did the lemma that this basis is orthonormal, which gave us the tracelessness as a result of the algebraic relations. And once we had the tracelessness, we kind of understood that the Majorana words, as opposed to Grassmann words, those are orthonormal operators. And once I had orthonormal operators, I had an orthonormal basis. I get an expansion of any operators in those Majorana words. And here we arrive in the Bravyi dictionary. So that's the important bit. Bravyi dictionary. And once we have this, we can, for example, compute the trace of two operators, and we will be using this in the future quite a lot in different ways. That's the first time this integral was non-trivial, because we had two objects, the dictionary entries of those operators, and this is implementing a non-commutative multiplication here plus the tracing. Okay. Good. So we finish here.